The last planning algorithm we're going to look at is called goal stacking or strips planning. The way this works, it's somewhat similar to the problem reduction planner in that it breaks down a goal into sub-goals and tries to achieve those sub-goals first. The difference here is that with problem reduction, we use our domain knowledge to break down a goal into sub-goals. But with the goal stacking planner, the way it works is more general, so it can be applied with less domain knowledge. And the way this works is that it knows of a set of actions that can be taken. And each action is defined as a set of preconditions that need to be true for the action to be applicable, and the action, and a set of post-conditions that will result once that action has been taken. And there's a special language used to define these conditions. For example, here in the initial state, this is the initial state, just the two disks on top of pole 1, and this is that state described in this language. It says disk 1 is on top of disk 2 is on top of pole 1, pole 2 is clear because there's nothing on it, disk 1 is clear because there's nothing on top of it, and so on. So in this language, in a similar manner, the goal can be defined as two components. We would like disk 1 to be on top of disk 2, and we would like disk 2 to be on top of pole 3, which is the target pole. So let's see how this algorithm tries to solve this. So the first goal is already satisfied because disk 1 is on top of disk 2. But the second goal, which says disk 2 needs to be on top of pole 3, has to be somehow satisfied by taking some actions. So the way the algorithm works, it considers every action possible that can take disk 2 to pole 3 from anywhere it could be, and it assumes that they are all satisfiable, they're all applicable, and then tries to satisfy their preconditions recursively. So here you can see that there are three actions selected. All of them are moving disk 2 to pole 3, disk 2 to pole 3, disk 2 to pole 3, but they have different originating poles. The first one says move it from pole 1, the second one says move it from on top of disk 1, and the third one says move it from pole 2. So recursively it tries to satisfy the preconditions of these actions in a DFS manner, and if it fails, it backtracks and goes on to the other action. And at some point, if it can achieve all the preconditions, then it considers the problem solved. So let's see how we can satisfy the preconditions of this action. So to move that, to move disk 2 from pole 1 to pole 3, these are the preconditions that need to be there. First of all, disk 2 has to be clear, meaning that there's nothing on top of it. Then disk 2 needs to be on pole 1 because we're moving it from pole 1, and pole 3 needs to be clear because that's the target. So in order to have disk 1 clear, again, we need to do something, and these are all the possible actions that have clear disk 2 listed in their post conditions. So this algorithm again goes through all these actions and just tries recursively to get one of them to be workable, and then this process is continued until at some point we can achieve both components of the goal. So we can just skip the rest and just go through this more quickly, and then somehow it managed to satisfy those components, and then if we execute the plan, we will see that it's been able to carry out this problem. So this is a simpler version because it has only two disks, and the reason why is that if we run this on the 3-disk problem, the algorithm can be caught in an infinite loop, and that is actually an exercise for you to change the goal stacking algorithm so that the infinite loop case doesn't happen. So we have looked at 3 different planning algorithms in OpenNERO, and that was planning in OpenNERO.